Hello everyone, I'm Paul and today we're solving problem 407, trapping rainwater 2. This is a hard one that's very interesting, or at least for me. So next I will show you my intuition, approach and efficient solution. We are given a height map, which is a matrix with the height of different cells in a 2D map. And we need to return the volume of water it can trap after raining. So if we are given this input, this is the height map, this is the visual representation, and this is the same. This is another representation seen from above. Let's say we are here, and the question is how many blocks of water can we trap? Well, let's see the neighbors. We have a 4, a 3, a 3, and water. So the minimum among these 3 is 3, so we can trap the minimum minus the current value, which is 2, meaning 1. Now we are here, so let's check the neighbors. We have this, 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 and water. So we can trap the minimum among these 3 values, meaning 3 minus the current value, which is 1. So we can trap 2 blocks of water. And finally here, let's check the neighbors. We have this, 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 and this. And the minimum among these is 3. 3 minus 2 is 1, so we can trap 1 more block of water. The sum here is 4, so we just return 4. Now let's step back for a moment. Let's say we are here again. And it's easy to say that this is the upper bound and it's greater than the current value. This is the left bound that's also greater than the current value. And this is the lower bound that's also greater than the current value. Now the question is, what is the right bound? It's, well, in this case it's this one, but let's say that here we have a 1, or here we have another 1, here we have another 1. So from this point, how do we know if this is water or not? How do we know what is the right bound? And the answer is we don't know. Similarly, if we are standing here, it's easy to say that this is the upper bound, this is the lower bound, but what is the right bound and what is the left bound? Because, for example, here 2 is greater than 1, but how do we know if this is the left bound? Meaning, how do we know if here we have to take 1 or 2 blocks of water? Because for this example, here we have a 3, so at this step we have to take 2 blocks of water. So the left bound here is this one. And how can we know this from this point? And the answer is we don't know. So the trick here is the following. Instead of checking for every bound from the center to every border, we are keeping track of every bound from the borders to the center. And by doing this, when we are standing here, we know that this, and this, and this are the corresponding bounds. So we will have a heap, and we are storing here every value in the border. We are using green for every value that's in the heap, and orange for every value that we have already popped. We will have a variable to keep track of the current level. We start from 0, and you will see why we are using this in a few minutes. So remember, we start from the border and we are moving towards the middle. Now we pop the first value in the heap, meaning the minimum value, so we pop this one. We could pop this or this instead, but let's say we start with this one. Here we have a 1 that's greater than the current level, so we can update this with 1. And here we have 2 neighbors, 3 and 4. And we have already seen these 2, they are part of the border, so we continue. Now we can pop this one. Here we have 2 neighbors that are already seen, they are in the heap, they are part of the border, and this is a new value. And we are checking if this is water or not. Here 3 is greater than the current upper bound, so this is not water. So we can add this to the heap and continue. Now we can pop this one. Here we have 2 values that we have already seen, so we continue. The next value in the heap is this 2. We could pick this or this instead, but let's say we pick this one. Here 2 is larger than the current level, so we update this with 2. Here we have 2 neighbors that we have already seen. They are in the heap, they are part of the border, so we continue. The same goes for these 2, and the same goes for these 2. The next value in the heap is 3, but we could pop this, or this instead. Let's say we pop this one. We have already seen these 2 neighbors, and here we have a new value. And this is smaller than the current value. So we can add water to the result. How many blocks of water can we add? Well, we do 3 minus 1. This is 2, so we add 2. And maybe you are wondering, how do we know that from this point we have the corresponding left bound to add 2 blocks of water to the result? Well, if we are using a heap and we have just popped the minimum value in the heap, which is 3, and this is smaller than the minimum value in the heap, well, this means that we have a left bound that's greater or equal to this 3. So we have the corresponding left bound to add 3 minus 1 blocks of water to the result. 3 is larger than 2, so now we are at level 3, and we add this to the heap. And the next value we can pop is exactly this one. We have already seen this neighbor, the same goes for this one and this one. This is the only new neighbor. And here 2 is larger than 1, but this is why we are keeping track of the current level we are at. We are at level 3. And this means that from this cell, we have 4 bounds that are greater or equal to 3. So we can add 3 minus 2 blocks of water to the result. This is 3. That's why we keep track of the level. If this is 3, this means that here we have a bound that's greater or equal to 3. This is greater or equal to 3. This is greater or equal to 3. And somewhere in the right, we have a right bound that's greater or equal to 3. Okay? Now we add this to the heap. The next value we can pop is exactly this one. And here we have seen every neighbor, so we continue. And now we need to pop one free. Let's say we pop this one. Here we have 2 neighbors that we've already seen. This is a new one. Given that this is smaller than the current value, we have water. How many blocks of water? Well, we have 3 minus the current value blocks of water, so we add 1 to the result. And just to make this clear, if this is smaller than the current level, this means that we have 4 bounds that are greater or equal to the current level. So we can add the current level minus the current value blocks of water to the result, which is exactly what we did. Now we add this to the heap. We pop this. We have already seen these 4 neighbors, so we continue. Next, we pop this and continue. We pop this and continue. The same here, same here, same here, same here, and same here. Finally, we reach the end and we return 4. So with this in mind, let's go with the code and hopefully you will get the idea. First, we say n is the length of height map. M is the length of height map at 0. And our heap is initially empty. And first we need to add the borders to the heap. So for I in range n, for j in range m. And now if we are standing at some border, if I is 0 or j is 0 or I is n minus 1 or j is m minus 1, heap q, heap push, and we are adding to h a tuple with the current value height map at ij, and we are adding the coordinates I and Shay. And now we have already seen this cell, and here we could use a set, but we are replacing the current value with a -1 instead. So we are doing this for simplicity. Here we can say height map I Shay is now -1. Now we can say our result is initially 0. We are starting from level 0. And while we have something in the heap, we pop the first element, heap Q, heap pop from H, and this will give us 3 values. We will call this height, I, and Shay. And first we can say if height is greater than the current level, the level is now the current height. You can do this, or you can say every time the level is the maximum among the level and height. It's exactly the same. Now we can iterate every neighbor, so we say for new I, new Shay in, and here we have I plus 1 Shay, I minus 1 Shay, I Shay plus 1, and I Shay minus 1. So for every neighbor, first we are checking that we are in bounds. So if an I is smaller than 0, or an I is greater or equal to n, or n Shay is smaller than 0, or n Shay is greater or equal to m. So if we are out of bounds, we continue. Else, we say the current value is height map at new I, new Shay. And if the current value is -1, meaning we have already seen this value, we just continue. And just to be clear, this is we are out of bounds, and this is already seen. Okay? So if we are still here, we are checking if the current level is greater than the current value, we can add to the result level minus current. Sorry. And every time we want to add to the heap, heap Q, heap push, heap a tuple with the current value and the new coordinates, new I, new Shay. And we have already seen these values, so height map new I, new Shay is now -1. And finally, after all of this, we can just return result. So this is the entire code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. This is out of bounds. And regarding time complexity, it will be big O of n times m times log nm. And this is because we are pushing and popping every value exactly once. And these operations in heaps require log n time complexity. So overall time complexity will be big O of nm log nm, and space complexity will be big O of nm. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.